Hello everyone, today I'm going to present this work, Handling the Positive Definite Constraint in the Bayesian learning rule. This is the journal with mark and empty. The Bayesian learning rule is an approach to unify Bayesian inference and optimization, and it is a natural gradient variation inference algorithm. However, it becomes expensive when you deal with constraints. In this work, we propose an improved Bayesian learning rule. It gives an efficiency update for the positive definite constraints by using Riemannian gradient descent. There are two different worlds in machine learning. In the Bayesian world, given data with latent variables, a prior and a likelihood, our goal is to infer the posterior approximation of the latent variables. Method using this world is known as the inference method. In the optimization world, we have decision variables, a regularizer, and a loss function. Our goal is to minimize the objective function to find the best decision variables. Methods using this world is known as optimizers. In this talk, we focus on the following challenges. Can we unify methods in both worlds? Can we use inference technique to design new optimizers? Can we do optimization with uncertainty? The Bayesian learning rule under the variational inference framework unifies many methods in both worlds, and it can help to design new optimizers, and it can also give an uncertainty estimation for the decision variables. However, it becomes expensive when you deal with constraints. As an example, let's look at Gaussian posterior approximation. The covariance measure of a Gaussian has a positive definite constraint. In this work, we make the following contributions. We introduce a new constraint parameterization. We propose a closed form correction term to address the constraint issue. Our approach can work on many useful approximations, such as Gaussian, mixture of Gaussians, and gamma. As you can see from these two figures, our method performs best among the others. Now I will give more details about this work. I will first describe the Bayesian learning rule, and then talk about the key idea of this work, and then give an example about a new rule, and conclude this talk with experimental results. First of all, let's review the variational inference framework. Given data D and latent variables W, our goal is to approximate the posterior distribution of W given data. Under the variational inference framework, we would like to minimize the negative elbow. From this expression, we can see that the negative elbow has two terms. The first term is about the likelihood term, and the second term is the KL divergence between the approximation and the prior. Here, the L function in the first term is the negative log likelihood, and the R function in the second term is the negative log prior. In the optimization world, the L function in the first term is known as the loss function, and the R function in the second term is known as a regularizer. From this expression, we can see that the variational inference framework bridges the gap between the Bayesian world and the optimization world. As an example, let's look at a Gaussian posterior approximation. In this case, we would like to minimize the parameter lambda, and it has two terms. The first term is the mean of a Gaussian, and the second term is the precision matrix of a Gaussian. The precision matrix is the inverse of the covariance matrix, and we know that the precision matrix must be positive definite. How can we handle this kind of constraint? One way is to do an unconstrained transformation and use existing gradient-based methods. This gives rise to black box variation inference. However, black box variation inference can be slow compared to natural gradient variation inference. As we can see from the figures on the right, the main difference between black box variation inference and natural gradient variation inference is that we use the Fisher information matrix as a preconditional. And here, F is the Fisher information matrix approximation Q. However, as we can see from this expression, that the natural gradient variation inference has a high iteration cost. The Bayesian rule is a natural gradient variation inference with low iteration cost. By choosing a proper constraint parameterization, we can re-express the natural gradient as a gradient with respect to an auxiliary parameter. By using this identity, we can obtain the Bayesian learning rule as follows. So if the gradient with respect to the auxiliary parameter is easy to compute, we have a low iteration cost. However, because we choose a constraint parameterization, we have to do a line search for the step size so that the update stays in the constraint set. This can be expensive in general. A quick summary of the Bayesian learning rule is that it gives a simple way to implement natural gradient variational inference, but it gives rise to constraint optimization. As an example, let's look at Gaussian posterior approximation. In this case, we would like to learn the mean and the precedent matrix. We define a new function L bar, and it has two terms, the regularized term and the loss function. And as we know that in optimization world, the L bar function is the objective function. And recall that we would like to minimize the negative elbow. By using this newly defined function, we can re-express the negative elbow as follows. It has two terms. The first term is the expectation of the L bar function, and the second term is the negative entropy of the approximation. By using the Bayesian learning rule to minimizing the negative elbow, we obtain the following update. It has two lines. The first line is the update for the precedent matrix, and the second line is the update for the mean. And let me remind you that if we use Newton's update to minimizing the objective function L bar, the update is as follows. From here, we can clearly see that the Bayesian learning rule gives a Bayesian version of Newton's update. Therefore, we can see that the Bayesian learning rule brings the two worlds closer, and in fact, that the Bayesian learning rule can recover many existing optimizers. For the details, please read this paper. However, because we know that the precision must be positive definite, it requires us to line search for the step size, so that the update stays in the constraint set. In this work, we'll address these issues by using Riemannian gradient descent. Before we talk about Riemannian gradient descent, we will first review gradient descent in a Euclidean space. Gradient descent can be viewed as a straight line as the step size varies, and it is the shortest curve. On the other hand, we can obtain a gradient descent update from a straight line. It requires two inputs to construct a straight line, a starting point and a Euclidean direction. In this case, the Euclidean direction is the negative gradient. Now, I'm going to talk about Riemannian gradient descent, also known as gradient descent in a Riemannian manifold. Here, the manifold is induced by the approximation Q, and X is the constraint parameterization. As example, let's consider Gaussian posterior approximation with constant mean. In this case, X is the precedent matrix. Here, F is the Fisher information matrix. We use it to measure the distance between 2 points in the manifold. To obtain a Riemannian gradient descent update, we will first construct a geodesic. A geodesic is a generalization of shortest curve in the manifold. Given the Fisher information matrix, it requires two inputs, a starting point and a Riemannian direction. As we can see, it is the negative natural gradient. Why do we need a natural gradient instead of a gradient? That is because we use the Fisher information matrix to measure the distance between 2 points in the manifold, and the Riemannian direction also characterizes length in the manifold. Therefore, the Riemannian direction should depend on the Fisher information matrix. Given these ingredients, we can construct a geodesic, and therefore we can obtain a Riemannian gradient descent update. And the geodesic is shown in the figure as the dashed curve. Now it is time to talk about natural gradient descent. As we can see that it is a straight line and is shown in the figure as the solid line. From this figure, we can make the following observations. Although the natural gradient descent is like a second-order method in a Euclidean space, it is a first-order method in a Riemannian manifold, and it is the first-order approximation of the geodesic at the starting point. Here comes the challenges. In general, it's difficult to exactly compute a geodesic. It requires us to solve a set of differential equations, and moreover, the natural gradient descent ignores the curvature of a geodesic. This is the main reason why the natural gradient descent update could violate the constraint. As we can see from this figure, as the step size varies, or if the step size is big enough, then the point will leave the manifold, which causes a constraint violation. In this work, we propose an approach to approximate a geodesic, and we show that our approach can efficiently capture the curvature of a geodesic, and therefore we can fix the constraint issue. We show that we can approximate a geodesic as follows. It has three terms. The first term is the starting point, and the second term is the negative natural gradient, and the third term is a correction term. It captures the curvature of a geodesic. And we show that this term admits a closed-form expression, and it can be computed by approximating the Christoffel symbols, which characterize the curvature of a geodesic. Moreover, we also show that under new constraint parameterization, we can efficiently compute natural gradients. As an example, let's look at Gaussian posterior approximation. The update on the left is the update derived from the original Bayesian learning rule, and as we know that it requires line search for the step size. On the right is the new update obtained from our new rule. As we can see that it has two additional terms. The correction term for the mean is 0, and the correction term for the preceding matrix is non-zero, and we can show that this non-zero term ensures that the update is always positive definite. So therefore, there's no need to do line search. Moreover, we show that both updates has the same time complexity in terms of big O notation. Moreover, our approach can work on many useful approximations such as gamma approximation, inverse Gaussian approximation, Rorschach approximation, and our approach can easily extend to mixture cases such as finite mixture of Gaussians, student T. The figure on the right is a finite mixture of Gaussian approximation. Here the number indicates the mixing components, and from this figure we can see that as the number increases, we get better approximation. Now I'm going to show you some experimental results before we conclude this talk. The first two slides is about full Gaussian posterior approximation. From these two figures, we can see our method showing red achieve accurate approximation and converge fast. The third figure in this slide is about gamma posterior approximation, and we can make a similar observation. We also test our method on several synthetic data sets. This slide is about finite mixture of Gaussian approximation. We first test our method on several 2D toy examples. Here, the number indicates the mixing components. And as we can see from these two figures, as the number increases, we get better approximation. And then we test our method on a 20-dimensional mixture case, where the ground truth is a finite mixture of student T distributions. We use a maximum mean discrepancy to measure the distance between approximation and the ground truth. From this figure, we can see that our measure showing red and black achieve the best performance. And then we also test our method on a 300-dimensional case, and our approach still work well. To conclude that we propose the input Bayesian learning rule, and it can handle positive definite constraints, and it uses natural gradients with low iteration cost. It doesn't require us to do line search for many useful approximations, and it's as accurate as the original learning rule, and it can be used to design new optimizers like the Adam-like optimizer. For the details, please read our paper, and if you want to learn more about this work, please join our section at ICML, and thank you.